So you've all been doing tutorials on your own and learning about Skyline, and now you're gonna get. I'm gonna actually, where you're gonna follow along and see how I use Skyline, and hopefully you'll learn a lot. I've had people say that that just the act of following along on a more complex data set can be very instructive. So what we're going to look at is we're going to look at a data set. Well, I guess we're going to be exploring this idea of refinement that I talked about on the first day, where we take you've now built spectral libraries and started to look into rent retention time prediction, and in this case, we're also going to look a little bit at this idea of an unrefined method, something where we don't know all the answers. Starting out, we don't know exactly what we're going to target. We actually started with quite a large set of targets, and I'll explain how we got those. And we take it into this targeted method refinement cycle, and the goal is to create a quantitative assay. And then this is the targeted method refinement cycle that we talked about before. There are a number of things that we can do in each time we go around this cycle, and we're going to pick up on a data set where we actually did sort of abundance and measurability refinement first. And so you're going to start with this pre-refined assay where what we're interested in is deciding, okay, which of the targets have any hope of giving us a differentiation. And so since our lab is not as wealthy as the Aerosol lab. The MacLean lab is not as wealthy as the Aerosol lab. We frequently are doing label-free and don't buy a lot of synthetic peptides. So our thought was, how far can we start with a hypothesis and take it through label-free before we get to the point where, okay, now we really have a set of things that we think might be a biomarker panel or something, and we're going to order the synthetic peptides and actually pay for them, but we want to do that for only the ones that we think are most promising. So yes, we're going to be in the differentiation phase. The data set is 14 salt-sensitive rats. It's their plasma, and we measure them in triplicate. So we're going to have 42 samples. And the way these unlucky rats were treated was, 7 of them lived nice lives. They were fed a low-salt diet, and they lived healthy lives until they were eventually harvested and their plasma taken. And then 7 others were fed a high-salt diet until they experienced heart failure. And then their plasma collected for these samples as well. And then the idea was to see what we might discover in the plasma that differentiated them proteomically. And we started with the hypothesis that, well, the 109 proteins reported in literature related to heart disease, people have already reported that they've seen differential abundance of these proteins based on heart disease status. So we decided we're gonna look at all of those. And today we would probably do this with a swath experiment because it's pretty easy to measure a whole lot of stuff early with a swath experiment. But at that point we really want to see could we do this with a triple quadrupole and SRM, and in fact at that point Skyline only worked for SRM. But we did get 109 proteins, and then we just took every possible measurable peptide, and that gave us 2,165 peptides, which we then, we took the entire y-ion series you can see here from Y3 to yn-1, which gave us 12,000 transitions, and we were able to measure that in an unscheduled way in 151 sample injections. And so there's lots of stuff that we would do differently now. We would definitely use IRT, so we didn't have to do these 151 sample injections. We would be able to measure this stuff. Well, actually, no, we're saying that we have no idea whether we can even see these things. So we do have to do these broad extractions of the entire gradient to see, do we see anything that looks like it might be a peak that explains our peptide. So we're not yet doing the the peak scoring that Ludovic is talking about. We don't have spectral data. We haven't ordered, because we didn't order synthetics. If we ordered synthetics, we could create a spectral library from the synthetics, but we didn't. We just said, okay, with a relatively simple sample prep, what do we think that we could see if we used a triple quadrupole, our most sensitive instrument at the time? And so some of them look like this. And you're basically going to be looking at the results of these, the ones where we could find anything. So we've been talking about sometimes there's two things that you might be able to see. A lot of times there's nothing. You look at it and you go, well, I don't see anything that could be this peptide. So this was a potential figure for the paper that this was going to be, but as you see when we start looking at the data, there were some problems with the data, so the data became a really great instructional tool, but never a paper. But this is the first phase, this refinement phase, which we called the detection phase, just figuring out what do I have a hope of detecting, and that 151 methods that took. And then what we're going to do is we're now going to do this differentiation phase. After the detection phase, we were already down to just 49 proteins that we thought we could detect. And that doesn't mean that we couldn't, go do immuno affinity purification and other things to try to detect all of these proteins, but it just meant with a fairly simple sample preparation, we felt we had any hope of detecting 49 out of these 109 proteins in the plasma. And then that was also 135 peptides, and resulting in about 780 transitions, which we were actually able to get down to measurable with a single injection. And this is with an older mass spectrometer. Newer mass spectrometers would have no problem with this in a single injection, but we created a scheduled method. And then our hypothesis was that we could then take this into a next phase, measure all 42 injections, 14 replicates 3 times, and then we would have some idea. I mean, some of these things, even though we think we can detect them, we'll see no differentiation. And so then we wouldn't go buy synthetics for those. But so there are going to be some that become our high-value candidates that go into the next phase. And that would be this validation phase where we would get much more serious about our quantification and validation and making sure that we're actually measuring exactly the right thing. So does anybody what happens if I make a mistake up in this phase and I'm not actually measuring the right peptide? I find a peak, right? I find a beautiful peak. I say, that's the best peak for measuring this peptide. I'm going to go measure it. But I don't have a synthetic. I can't prove that that's my peak. What happens in this next phase? It's probably not different. So we hypothesize, well, those things are just going to fall out. And what if it doesn't fall out? What if there's this amazing difference? Well, it's just like a gel, right? Okay, now you have an amazing difference, and you go order this, or you go, wow, this peptide's the biomarker, and you order the synthetic, and the synthetic says, nope, the peptide's way over here. And whoa, what was I looking at? Well, we have tools. We're mass spectrometrists. We have tools to figure out what is that peak. We can do de novo sequencing. We can do lots of things to figure out if it turns out to be the highest value biomarker in our sample, we're going to figure out what it was. So there was relatively low cost to not quite quantifying the right peptide, although we thought that we were probably, in most cases, quantifying the right peptides. But this differentiation phase was kind of interesting. All right, so this is 49 peptides. I think you've seen this before. This is the scheduling view. So this is us scheduling this all into. We did 6. Once we were down to 780 transitions, we did 6 unscheduled injections and scheduled everything, and then we had a single injection. So as a review, the experimental data is this rat plasma experiment collected by Daniela Tomazella at the University of Washington, 14 subjects, technical triplicate, so we have 42 runs. The proteins, our targets came from literature. That's a pretty common source of targets for targeted proteomics. There's no labeled reference peptides. We didn't have much spectral library coverage, which is why when you open this data, you'll see that not every peptide we have a spectrum for. And so that's why we also chose to just measure the entire Y-ion series. So exhaustive measurement of our triptych peptides, our Y-ion series, and then refinement. So, and then we're going to take some quick looks at the data just in slides, and then we're going to get into it live. But I want to get across this. I actually was talking to somebody else about this a little bit, one of the people in here in this group with the other data. And we've definitely mentioned how important prior knowledge and consistency are to targeted proteomics, right? And a quote I heard from Rudy Ebersol really early on in my involvement with targeted proteomics was, we need to stop rediscovering our samples every time we run them. And one of the important precepts of targeted proteomics is that you can become familiar with what you're measuring, and you can store information about what you're measuring and reuse it over and over again, and you can get better measurements because of that, rather than just sort of passing the data always the same way through tools that don't know anything about it. So this prior knowledge is based on empirical measurement, and it's powerful enough to be used across labs, but and across experiment. But it's even more powerful run to run. So if it's powerful enough to be shared with somebody else in another lab, it's even more powerful when you do 42 runs right in sequence on the exact same instrument. And so those physiochemical properties that we share lab to lab, but you're going to see are very powerful for looking at your data, and you've already been seeing it, are relative ion abundance. And the way we share those is putting them in spectral or chromatogram libraries. But as you've seen in a few cases already, relative ion abundance across a set of samples is a really powerful way of knowing that you're measuring the same thing over and over again. And retention time, we share it by using IRT. But retention time, again, we don't expect peptides to be changing their retention times all over the place when we're doing an experiment. If we see that kind of thing, then there's some problem with our instrumentation. Optimal collision energy, which we haven't looked at too much here, but there are other properties of peptides that we store and can use over and over again, and that we take advantage of as mass spectrometrists. So this, you've probably seen some plots a little bit like this. This is, the top plot is what Jake showed, where you just normalize all of the peak areas to 100%, and then you get the relative distribution of the various fragment ions. And then down here is the retention time plot. But let's focus on this first plot up here. What do you see about this plot? Is there anything noteworthy about this? Sure, go ahead. What? Oh.
I mean, in none of the samples is really matching to the library. Complete. I mean, the library really is the one sample, you can say, which is different from the others.
Okay, so that's a good eye. Yeah, so we see that it's I mean, they match pretty well, but yes, there's definitely Y4 and Y3, the two least selective ions are underrepresented in the library and overrepresented here. So that's one thing. I mean, I think it's not terrible, but yeah, it's not a perfect match. But again, do you have any idea where this library came from? It's just a public library. None of us know where it came from. So it's not you'll see cases in this data, and that was part of the point was that we didn't have library data of our own. We didn't order synthetic peptides. We didn't measure on our exact instrument. We just went out and saw okay, what's in the peptide atlas and what's in the human or the global proteome machine, and those are the spectra we have. I wouldn't put too much stock into the fact that they don't match exactly. I think to me this is a close enough match to say it's pretty good likelihood that these measurements are the same as that measurement. But I don't know. Okay, how about, so I guess I've annotated it here. These are all the runs of our diseased rats or heart failure rats, and then these are the healthy ones. Anybody see any difference between the healthy side and the disease side? Go ahead.
So in the disease, there are maybe 3 samples which look a little bit worse. So one could check whether there's some interference or something else.
Okay, so maybe this one, this one, this one. And then generally there's more variance over on this side and less on this side, right? And so this is a thing, when you look at a lot of these plots, you're going to start to, so in the next slide I'm going to denormalize this. Can anybody guess what's going to happen? So I'm gonna let you see, right now I'm just showing you the relative abundances. When I let you see the absolute peak areas, anybody have any idea what's gonna happen between the healthy and the diseased? What's gonna happen?
Probably disease is gonna be lower.
Yeah, disease, that's probably why we're getting so much variance, is because we're very low abundance. So when we see lots of weird variance, it's generally an indication of lower abundance. So that's what it looks like. And you can see that there's a fair amount of variance over, I mean, like in the absolute peak areas are not exactly the same over on this side. So it's kind of amazing that, you know, it's this consistent. The relative abundance is that consistent when the absolute abundance is changing that much. But when you really get down to, you know, what this is probably a 20-fold at least change, then you get down to low abundance and things, and you get all that variance. I want to actually quickly just go back to the retention time side of things. Does anybody see any problems in the retention time? Yeah, go ahead.
The retention time looks very different also inside if we consider just only the replicates.
The retention. Sorry, what was the?
There are some fluctuations inside the retention time among all of the samples, but also if we consider only the replicates, right?
Oh, okay, yeah, okay, that's kind of interesting. So she's saying that, you know, there's variance among the retention times here, but then also if you look at the transitions, I think you're saying.
No, the replicates. If we consider the replicate 1, 2, and 3, different, right?
The replicates of each subject, the retention time's changing. So we're going to get into this a little bit later, but like I'm plotting this without any, you don't know the time, you don't know the order that these were acquired in, right? Anybody, like, what would you like to see? If I were to, so these are ordered logically. So I've grouped all the diseased on one side, all the healthy on another side, and then I've got like each subject. What would we like to see when we get rid of this logical grouping in terms of ordering? What would be the best ordering for these replicates?
Yeah, as you said, the order of the measured, right?
What?
The order of the measurement. I mean, because then if you see an increase over time, that's okay, I would say. If it's not two-step.
So yeah, what would be the ideal order of measurements for these replicates? Is this a good order? Would this be a great order to measure my replicates in? All the disease first, and then all the healthy second, and every subject grouped together.
Okay. Scrambled maybe?
Yeah, there should be definitely some randomization, and that's something that when we have Olga Vitek here tomorrow, she's going to try to hammer into you good and hard. The other thing is we'd like to see cycles so that we're doing some blocking. We would like to see, you know, that we actually measure all of our subjects once, and then we measure all the subjects again, and then we probably randomize within those groupings, right? So anyway, so this is not actually the true order that they were measured in, which is one reason this one might be popping out, because it might actually be measured right next to this one or something like that. But it turns out that when we look at this data, this one always sort of pops out a little bit. I don't know what happened something happened in the chromatography. It's always a little bit out there, and that again, that's a consistent thing. You would, if we had IRTs, we could normalize to the IRTs, and these would get very, very straight across. But this is pretty good chromatography. There's not a big problem here. Okay, so here is denormalized, and then I've given another peptide for the same protein, this haptoglobin protein. These are the two peptides we measured for it. They're both co-regulated. They both, are, if we look at statistical significant, they're statistically significantly down-regulated in the disease. This is a good biomarker candidate. So here's another peptide where things get a little bit more complicated. And in fact, the first time I presented this data set with Olga Vitek and her graduate student, Mina Choi, who is the main person behind MS Stats, Mina gave this as an example of something you should just throw out because there's so much variance over on the disease side. But if we looked at the healthy side, it's got a little bit more variance than we saw last time, but it's not terrible. And then, the retention time on the healthy side is also reasonably okay. Here it's kind of a mess. So what would you like to do? Can you make a decision yet? Not really. So this is why Skyline's ability to do directed interrogation is really important. So we want to be able to look at the chromatograms and see if we can understand what's going on. Well, first we'll denormalize. And the thing that makes this even a little more, I guess I already gave you a hint last time. If you see higher variance on one area and lower variance on another, it's probably because it's a change in intensity. And so here we go. We have nice amount of peak area over here and almost nothing here. And then I've included the one other peptide that we measured for that protein. And in this case, they're inversely regulated, right? This is probably not statistically significant, but this one is upregulated in the diseased and lower in the healthy, and this one is clearly fine in the healthy and just about absent in the diseased. But we want to go look at the chromatograms because maybe there's just some problem that we really should throw out this peptide. This may be a case where this isn't really the peptide we think it is. But is it a peptide? Because if it is, it's a potentially good biomarker. So this is what the data looks like when we go look at the chromatograms, and it's not fantastic, but basically every healthy run looks kind of like this, and we do see coelution of at least 5 transitions, which is pretty good. It's definitely a peptide, so there's some peptide there, and when we look over here, this is my best attempt to integrate something that looks like this. It's really very close in retention time. It's so low in intensity that maybe we don't really get great coelution, but basically the relative intensities are kind of right. But then if you look at zoomed out the entire 5 minutes that we measured, you can integrate the entire range, and you wouldn't have as much peak area as this. So there's nothing else there. So then the only other question is it possible that we just didn't capture this in our window? Especially if we measured all healthy and then all diseased, maybe we had a chromatography change in between, and that peptide is just absent. It's just not inside this window, so it's not measurable. So this is now this is the acquired order. So this is the order that the samples were acquired in. It's very easy to achieve in Skyline, and just a right click and you can choose from a menu. And yeah, I was disappointed to see this order because while it does have cycles, you can see that all the diseased are measured, all the healthy then measured, all the disease measured, all the healthy measured, all the disease measured. So and in fact, if you look, 102 is the first disease, 102 is the first disease, 102 is the first disease. So it's exactly the same order in 3 cycles. So this is one of the problems with the data set. There's no randomization, but at least it's in cycles, and so it's hard to believe that we could have been changing the chromatography so that this peak disappeared and then it came back and then it came back and then, you know, so at least we can guess that it's probably not, you know, there. If there's nothing there, it's because there is no peptide to measure. On this counterexample that now we're gonna start looking at the data ourselves, and you're gonna get to start seeing some of this. This is a truncated peak. This is a peak that's drifting outside the window, and we're gonna see some more examples of this in the data. This is another one of the problems in the data. The retention time variance was more than the 5 minutes that we gave it for this window. One of the other great things about swath DIA is you don't have to worry about this because you always have the entire time range. But when you're scheduling, if you choose your scheduling windows too narrow, you can lose your peak. But this is what it looks like. It doesn't look like this. And so I would say, if it were me, you know, this is our differentiation. I think that this peptide, or whatever this is, I think it might be this peptide, but I would order the peptide and start investigating this peptide. This would be an interesting peptide to follow up on. So, and you can learn all of this stuff just by sort of directed interrogation with Skyline. And I think that's it. Yeah, so let's get to the data. So everybody should have their thumb drive. You can plug it into your computer, and we're going to grab the data set. There's actually a full tutorial on this data set now. For a long time I was teaching this data set, and there was no tutorial. But if you haven't been looking at I mean, I have seen some people looking at the Skyline website. If there's an incredible wealth of information up here. And so one of the really important places is this tutorials area. And you know, here are a whole lot of tutorials. So once you get done with the tutorials you're doing for here, I guess they show up down here. This is I'm going to change this to say ETH course. But those are the tutorials you've been doing. But there are lots of other tutorials that you could do here. And this one is group study data processing. It's 70 pages long, goes into excruciating detail on this data set. We won't go quite as deep as this goes, but you could then go do that if you want to. All right, so, but now you can off the thumb drive. So there's mine. Inside tutorials, you get group studies. I'm just going to grab it and drag it onto my desktop. I know some people have had problems with the desktop, and so if you want to grab it and put it in your documents folder like here, that's also fine. But if you have had success with the desktop before, go ahead and drag that onto the desktop. And it should come across reasonably quickly. It's still it's SRM data, and all SRM data is smaller than DIA and PRM data, so it's going to come over quickly, more quickly than that stuff. This Skyline flash drive, everybody's welcome to take, I guess, both flash drives you got for this course you take with you. This Skyline, the flash drive, the blue one, has all the tutorial data for all of the Skyline tutorials up here, plus a few extra things like this IRT or this IPRG data set and the PRM data set from Jake, and it's got PDFs for all the tutorials too. So you don't actually even have to go to the website now. You have a copy of everything. Okay, so let's go ahead and take a look at this folder. So inside the folder, you'll see this heart failure folder. And inside the heart failure folder, there is a ratplasma.sky.zip, and that's a shared Skyline file. And has anybody shared a Skyline file yet? Okay, we got one person. Okay, well, we're going to do it. Don't open this because that's the fully processed data set that we'll start looking at the end of this. But we're going to go into here, go into this raw folder. And here you can see a collection of MZML folders, or MZML files rather, which all originated from thermo raw files, and I just turned them into MZML files because they import more quickly, so they're that makes them better for this tutorial setting. but certainly Skyline could just as easily import the thermo raw files as it has been the WIF files that you've been working with. So down at the bottom here is a ratplasma.sky file. And okay. Yeah, I guess we'll just go ahead. You should be able to just double click that. And in my case, I don't have an association, so it won't let me do that. So let's see, does it show it? No. Okay, so in my case, I can't do this. But how many people did it work for? All right, okay, well, if it didn't work for you, I don't even have Skyline on here. Boy, have I. Okay, so if you, like me, don't have Skyline on here, no, you probably, I'm sure you all do. So if I go to this, if I go to my flash drive here, then there's also installers on here, and so I can go ahead and quickly install Skyline. That should go pretty quickly. Are you kidding me? What is going on? Huh. All right. Install Skyline. Ooh, we're still getting. Okay, so there it is, Skyline for me. I'm gonna just go ahead and open that on my desktop. Group studies, heart failure, raw. Okay, so if you got through Skyline any other way, go ahead and open up this ratplasma.sky. And then you'll see this. And you can see down at the bottom, there's 49 proteins, 137 peptides, and 789 precursors. So I said 708 or 789 transitions. I said 780 transitions for those peptides that we had, which I guess actually I said 135 peptides. So what are these extra peptides? Let's look at the bottom. At the bottom there are 3 peptides, each with well, they're not. It's not in a consistent number, but 6, 7, 4, can we turn down the sound so that we don't get the feedback? Okay. So, but anyway, so this is where the extra transitions are coming from, and it looks like we lost one peptide along the way somehow. I said we had 135, and here we have 134. These are the standard peptides. The goal of these peptides was to use them as normalization peptides. So we don't have labeled reference standards, so the goal was that we would be able to normalize by some peptides that we injected into the sample. A common thing that we do in non-targeted runs is to normalize maybe to the median or normalize to the TIC, or there are things that we normalize to in DDA experiments. Why wouldn't we do those in targeted experiments? Anybody have an idea? So why shouldn't I just take the median? I measure all these peptides, I just take the median peptide and normalize everything else to it. That's something that people do in DDA experiments. So if I'm doing a big label-free experiment with MaxQuant or something like that, I can. Why wouldn't I do it for targeted? Do you have an idea?
Would you to normalize on. And
Yeah,
in this case,
so-
we have a lot of things which are not there in the disease. That's
Right.
I think that's-
So the assumption then is that the median or over half of your sample is just stuff that's not changing, right? Same with TIC. If you measure against the TIC, your assumption is that most of your signal is from things that aren't changing. And when we do a targeted experiment, we've narrowed down to things where we hope to that they're all changing. Our goal is that these are all changing. That's what we've been targeting. So if we pick something, we might completely normalize away the effect, or if that peptide happened to be experiencing a change in the different direction, we might exaggerate our effect. And so in this case, we inject some peptides that we intended were going to not change at all, and then any changes we saw were due to systematic changes in the mass spectrometry, and we were going to normalize against them. Okay, so let's get going and import some data. So file, import results, and then click OK. And then if we select, if you're in the raw data file, if you're not in the raw data file, you want your desktop, group studies, heart failure raw, and then you pick all of these by clicking and then shift clicking, and now you have them all, and you click open, and that's your 42 runs that are going to start importing. And this is, they import very quickly. You can hide this window if you haven't ever hidden it. You can hide it, and then you can bring it back up at any time by clicking on this little graph in the status bar here, if you're quick enough. There it is. Okay, now it's gone. Okay, so on my computer, everything has been imported, and I can click on this first peptide. Yes. Yep.
Getting the list of proteins and peptides is important because you don't care for the rest, and you limited this through the import, right? When you would put your FASTA or put your peptides. So actually, was this most straightforward way to get only those proteins and only those peptides and throw out the rest?
So yeah, in this case, we chose 109 proteins, right? So I didn't actually do this, but I suspect that the person who did this, there are a number of ways that you could do that. You could create a collection of accession numbers, and then you could go to, if you had a background proteome. Have you guys set up a background proteome?
Yes.
Okay, so if you had a background proteome and you had a list of accession numbers, then you could go into edit, insert proteins, and you could paste in your list of accession numbers, and SkyJam would just find those in your background proteome. You could also just paste in the list of names, and that's one way. I suspect that this was done early enough in SkyJam that what she did was use resources to collect a set of FASTA sequences. So I can go to UniProt and I can find a protein, and then if I scroll down, there's a place where it gives me the FASTA for that protein. I can copy that out and create a collection of those in Notepad or whatever, and then that's what I can import as my FASTA, or I can just paste it right into SkyJam. So that's how I expect that this original document was built.
And the peptides?
The peptides. So the peptides come from, again, the peptides originally it was the full set of peptides, every peptide for the protein that was within a certain size range that we could capture it in the mass spectrometer, and that was the original set of multiple thousands of peptides. And now this has gone through one iteration of this abundance check where, Daniela looked at everything and looked for any sign that there might be a measurable peptide.
So you've been deleting peptides, and this is the final list.
Yeah, this is the final list. So she's already gone through and looked at the full gradient chromatograms of every peptide. And let's go ahead and do that for this peptide, and we'll see whether we think Daniela did a good job in this case. But let's arrange these windows a little bit. You have some experience with arranging windows. I'm going to show you my favorite arrangement, especially in this limited screen real estate that I have. is to grab onto the targets window. So click on the title that it says targets and just pull it off until you get this blue rectangle, and then release. And so now that's just floating up above everything. And then you'll take that, you just leave that there for now. And then I'm going to take the retention time window and dock it to the bottom. So first I just click in the title of where it says retention times, and that gives me this blue rectangle. And then if I drag my cursor down so that it goes into this square down at the bottom of the window, so that I get this blue line, this blue bar across the bottom. Everybody got that? And then you just release, and it docks. And so now we have that, and then we can take the peak areas and make the peak areas share the space with that retention times by grabbing the peak area window and dragging it till we get this blue rectangle, and then drag it down into the retention time space until we get this cross, and we'll just put it to the right side by putting the cursor into that right hand rectangle and that cross in the middle. So that should, then you get a blue band that goes across the right side. And when you have that, you can release. And then finally, we're going to take the targets and drag them till we get a blue rectangle, and drag the cursor to the left side of the window until we get this blue thing that's up above the retention times and peak areas, and let go. And then finally, I'm going to take this library, so you can see the difference. There's different kinds of windows, right? There's windows with these tabs, which are mostly the chromatogram windows, and then there are windows with these title bars that are either gray or blue, depending on whether they're selected. So we're going to take this library match. It's currently got a tab, and we're going to turn it into a one with a title bar by clicking on the tab until we get the blue floating rectangle, and then drag over to the right side until we put the cursor in the right side box, and we get a blue rectangle that extends across the whole thing. And then we're going to release. And so now we have the chromatograms in the middle, the targets on the right, and the library or the targets on the left, library match on the right. And then we have the retention times. Our big multi-replicate views extend all the way across the bottom. And then I'm going to click this push pin that shows me the tip auto hide for library match, because we're not actually going to use this library match view a lot in this data processing, so we just get it out of the way. Anytime I put my cursor over this tab on the right, it kind of slides out, and it slides out full length and gives me a view of that spectrum when I want to look at it. I can resize any of these views by coming to the edge of the view, and then this cursor changes to a little splitter bar like this. You see the two arrows going left and right, and then I can go like that, and now I get a better view of that spectrum. And it's there for me when I want it, and it goes away when I don't want it. Okay. So if we got, one more thing you've all already done. We're going to go to View, Arrange Graphs, and if I could say tiled, and Skyline would dutifully tile everything, but I wouldn't be able to see anything because it's 42 replicates. I don't have enough screen real estate for that. So I heard some people saying, "Oh, it's really good to have big monitor." So this might be a great excuse to go home and convince your boss to get you a really big monitor or two monitors that you can spread Skyline across. But we're going to go ahead and do Arrange Graphs Grouped, which you've already done. We'll do 3 panes. We're going to choose distribute graphs among groups, which is sort of like dealing a deck of cards, and that will give us each subject will be spread across all 3 panes. and we're going to go display in a row, so across like that. Our sort order is going to be document order, and then that's all we need. So we then just click OK. If everybody look like this, is anybody behind at this point? Okay, so click OK. And now we get our 3 views, and you can see that if I go to this replicates drop-down list above the targets, I can see all the replicates, and if I go up to the top, I can click on 102, and then if I click down arrow, press down arrow on my keyboard, 1, 2, now I have the 3 102, the subject 102, there are 3 replicates on top. It's a little bit hard to read right now because I've got this big legend here. Has everybody gotten rid of this legend? Is there anybody who's gotten rid of this legend? Okay, one person got rid of this legend. Well, I would say that usually when I've got all these things showing, I really only need the legend once. And so I choose a view, and in this case, somebody appears to have chosen this peak areas view because the retention times view in my case doesn't have that legend anymore. So in each one of these plots, in all of these plots, it's important to know that there's a fair amount of useful things on the right-click menu, and you maybe have discovered some of those already. But we can turn off the legend for chromatograms in here. So right-click on one of the chromatogram plots and click legend. And that will get rid of the legend. And in this case, that's pretty nice. I'm going to I think the font is a little bit big. It's nice to have it a little bit big because that makes it more readable, but I think given the amount of screen real estate we have, this is too big. So I'm going to right-click and press Properties. And you can see that these are font sizes. There's a choice of extra large, normal, small, and extra small. And this is actually something that my very own 15-year-old son added this summer while he was working in our lab. And so we're getting him back this summer. He's going to add some more great features to Skyline. But so I'm going to go down to large size font. And that scales it down a little bit. It's not quite as big. And then if you are showing a legend across retention times, you can also right-click and turn off that legend like I just do now. Okay. So look at this first one. What do people think of this? Do we think Daniela did a great job and this is a really beautiful example of a peptide? Nobody wants to say anything bad about Daniela, right? She did a great job. But this doesn't appear to be very measurable. Again, it's pretty different from the library, as somebody pointed out before. One thing about these docked windows is I can double click and that will pop the window out. So I can make it fairly big so you all can see it. And then I can double click and it will pop back into its place. So let's take a closer look. And we can see some patterns here. There does seem to be something. It's very different from the library, right? The library, the most consistent pattern has a lot of Y4 and a lot of Y3, which I think I mentioned are the 2 least selective transitions. So this just immediately, if you get used to looking at this kind of data, that's kind of a red flag that the dominant things are Y4 and Y3. Probably means it's not coming from this peptide, and it's not very consistent. And if we look at the retention times, we can see that if there's anything, it's this thing that's at about 18.5, right? There's a bunch of stuff that's getting picked too far away to be the same thing, but we can click on a few of these. That might be a peptide. Another thing we can do is right click in the peak areas, and if you actually is everybody normalized does everybody have that normalized plot, or should we go over how to get that? So if you didn't have normalized to total, the way you would get the normalized plot that I've been looking at and talking about is to go to right click in the peak areas view and normalize to total. And then we're going to now denormalize by going right click, normalize to none. And so now we can see, so frequently when you have some questions about a certain peptide, it may be most interesting to see, well, what does it look like when it's the most intense? So we can click on some examples of high intensity. And wow, do we see, how many are we supposed to be seeing? Do we see 6? Does anybody see 6 co-eluting transitions? No. At best we see 2, right? And what are those 2? Y3 and Y4. So like if somebody brings one of these to a lab meeting and tells you like, oh wow, I found this peptide and it's really, like, tell them to go order the synthetic and prove that that's the peptide, because my guess is this is not the right peptide. But before we delete it, we're just going to get rid of it because it doesn't look like it's really very consistently measurable and it's not going to make it to our next round of refinement. I want people to notice something else about the retention time view. I'm going to pop it out here. And so what do you notice about the retention time side of things? Anybody have any? Well, other than it's all over the place, there are these gaps, right? So, and that just means like Skyline chose not to integrate those regions, and this is what I call refinement view or refinement mode. And so Skyline, when you're in refinement mode and you've got all the Y-ion series selected, Skyline attempts to help you out by dropping certain transitions that it doesn't feel like, well, these transitions aren't all really co-eluting. So it's saying, it says, oh, I think, here's a case where all 6 are maybe co-eluting, but here's a case where, well, there's probably only 4 things that are co-eluting, and this other thing doesn't really look like it's co-eluting at all. So this is useful for the previous refinement mode where we measured the entire Y-ion series, and we might want to go to edit, refine, advanced. And in Edit, Refine, Advanced, we can there are ways that we can tell Skyline to just delete all of the bad transitions, and we're working on better ways to tell Skyline to do this and better ways for Skyline to detect this. But that was what we implemented, and so this is in refinement mode. It comes from a refinement experiment, so maybe it should be in refinement mode. But we're about to do quantitative mode. We really want to be able to say something quantitative about these things, and in that case, if we allow Skyline to just kick out transitions when it doesn't feel like they're matching well enough, that just messes up our quantitative statistics. So the way to switch to quantitative mode is to go to Settings and choose Integrate All. And then now you can see that everything gets filled out. So Skyline by default will give you a peak area for every transition. So that's a good, if you see retention time plots that are not completely filled out, that's a good indication that you need to go to Settings, Integrate All. Okay, so if I double click on the title bar of retention times, it just pops into this view. And now I think I can go ahead and delete this first peptide. It's not good enough to make the next round. This next one, however, looks a lot better. Let's flip it back into the fully normalized peak areas. So right click in peak areas, normalize to total. All right, and so now this is the mode where I think you can actually progress through, like definitely, as Ludovic said, boy, and you would definitely like to have the statistical tools that Ludovic was talking about, but that doesn't mean that you should ever give up looking at your data. Because I've seen many times where people get so focused at the statistical level that they forget that they have complete access to the data beneath, and there are actually problems in the data beneath. So always protect your ability to get in and look at things. So in this case, so are we done? Is this one all integrated perfectly and we nothing to worry about? Or does anybody see anything that we should look at? Yeah, this one over here, the in the retention time, it's kind of like, yeah, I mean, so what we're going to be doing a lot of now is looking at these summary plots that we have so nicely arranged and going, okay, which one's not like the others? It's that old, Sesame Street game. So here is this one. We click on it, and it's, that definitely does not look like these other ones. How would we get to see, so it's not in the right time either, so how would we get to see what's going on at 30.8? Zoom out. So here's the most important key combination in Skyline, keyboard shortcuts. There are quite a number of keyboard shortcuts in Skyline, but the most important one is F11 and Shift F11. F11 will zoom you in, and Shift F11 will zoom you out. So there we go. So we're zoomed out. Another way that we could figure that out, I'm just going to zoom back in by pressing F11. Okay, another way, what's another way? We can synchronize zooming. So if you right click over here, this one's already set up to synchronize zooming. If you haven't done synchronized zooming, actually Tina Ludwig was the inspiration for synchronized zooming. She kind of asked for something and I went, oh, I can give you that by synchronized zooming. So we added synchronized zooming. If you don't have it checked, click here and check it. And then once you do, you can now select one of these tabs where you can see the peak. And if you just, either you can use Control Click to pan a little bit, or you could use your mouse scroll wheel to change the zooming a little bit. And then all of the views will snap to the same zooming level. And so then we can see over here on the left side, there is, at about 30 minutes, you can see that the peak is coming in right at the edge of the scheduling window. And in this case, it's been truncated. It's cut off. It's our first evidence of truncation. And so now we're just going to integrate this peak. We have two options. We can either just remove integration completely by right-clicking and saying remove peak. And that creates a blank spot here. Or we can reintegrate this by clicking underneath the x-axis. Has everybody done this by now? Click beneath the x-axis and drag the range. So you click at one edge of the peak and you drag to the other edge of the peak. And that's how that's the easiest way to change integration for something. You can also, if you bring the cursor over these dotted lines, you can see that it changes to an east-west arrow cursor, and you can adjust things that way too. But I generally mostly do this kind of reintegration. Okay, so there's one peak fixed. What's the concern here? So I integrate that peak. Do you have any concern about that? What about the statistics? If I do statistics and I use that peak area, is that a valid peak area? No, it's not a valid peak area because it's not, it's not a full peak area. What if I had an internal reference standard? Would it be a valid peak area? Kind of better. It would be better, because then every point in the peak is a valid ratio. And so as long as I'm using ratios of references that are co-eluting perfectly, then I can still get a valid measurement for something that I don't have, the entire peak for. But in this case, since it's label free, this peak area is not representative of the peptide that I was trying to measure. So it's a bad idea to use this. So if you're going to use a statistical tool downstream that doesn't understand truncated peaks, and now in the latest version of MS Stats it does, and certainly in Skyline it does, it will just throw away truncated peaks as not usable. But if you're going to go take it to some other statistical tool and you're not sure about that, then you really want to go and do remove peaks so that you have no value, right? Because then you basically, the statistical tool has to deal with a missing value. Okay, but since we're going to be using MS Stats and Skyline, we go ahead and with impunity integrate these truncated peaks, and we know that the statistical tools will deal with it. Okay, so what else should we look at? How about anybody? Anybody? What else? Is there anything that doesn't look like the rest?
There is this replicate free D103.
Which one?
This one.
This one? What?
No, on a level. The replicate free of 103.
103 replicate 3. Yeah, exactly. So this totally does not look like the other ones. So we can then just click on it. And what happened? Again, we've got truncation, and Skyline picked the next best thing that it could find. And so, again, if we want to integrate the truncated peak, we just click and drag beneath the x-axis, and now we've got an integration that looks much more like the other ones. Is there anything else anybody wants to look at? I would say, okay, so now we now know that the scheduling window ends pretty close to 30. So we can kind of look along here and guess what other replicates might be truncated. So we just did this one, and we've done this one. Anybody have a guess at another replicate that could be truncated? The last one. Yeah, okay, let's take a look at it. Yep, it is. So in this case it was truncated. Skyline picked the right thing. And let's go ahead and look at view results grid. So this is a way to look at the results, the numerical results for every element of the currently selected thing. So in this case, we've got a peptide selected. We can see this peak found ratio, peptide retention time, and our ratio to standard, which is NA. If we now zoom in, we could click on so expanding that peptide, we could click on the precursor, and we get a bunch of other new values. There they are. So that we have full width at half max, start time, end time, total area, it's max height, etc. And if we click on a transition, then we get a bunch of transition values. And we also can write notes about them. So here's an editable field where we could write notes about each thing. So let's go ahead and add so these are all customizable views. Skyline has a number of customizable views, and we're going to export some reports, but let's go ahead and customize this view by going to click on the views menu up here. And so we're looking at precursor results, and let's go customize view. And now you can see all the precursor result values. You can see the ones that are here already. We've got we don't need isotope dot products. So we'll just call this view SRM precursors. So let's see, what are some other things we might want to get rid of? You know, maybe I don't really care about the max FWHM, so I can select that and click this X button to remove it. Area ratio, we can actually call this SRM label free precursors, and then we can get rid of total area ratio. Maybe we don't really care about the maximum height. And maybe with this peak found ratio, we don't, that's not that interesting to us. That's about how many of those things Skyline would kick out if it were trying to measure coelution. So we can get rid of that one too. So we have a little bit more manageable list now. One thing we'd like to add is, where is it? Precursor. Well, I guess I can click here. So there we go. Okay. So there's a little find button. If you have trouble finding something in this list, this is the list only for precursor results. When we go to edit reports, it's even a bigger list, and you go like, oh, what was that thing? So you can always click this set of binoculars up here, and I just typed truncate, and that got me down to this count truncated here. So, oh, that's now drilled all the way into, well, precursor. Okay, I'm going to go to the other count truncated. Here we go. So, so if we check the count truncated, and you can see that Skyline has put it sort of where my cursor was. You can use these arrow buttons to move it around. I'm going to leave it right next to the note. The other thing I'm going to do is click and shift click the area and background area, which are things I'm really interested in, so I want them a little closer to the front. And so I can select them both and then click the arrow to move them up. So they'll be right after count truncated. Okay, so there's my new results grid view. Is anybody still with me? Okay, so if you're not with me, this is not super critical. Like you could have gotten totally lost, and we're gonna move on, and you won't be like, oh, I fell behind. So this is just kind of fun to start playing with these grid views, which give us immediate information, numerical information, extremely useful information, and it's very customizable. So when we decide, oh, this is the most useful way to look at this, you can do it. And so this is in the results grid. So we click OK. And here we have, and we can see count truncated, right? And so now I asked you the question of how many of these replicates did you think were truncated? And we were able to pick 3, but there's actually a few more that are truncated. And we can get the full list by clicking on this, the header that says count truncated in our view now. And we can sort descending. So when we click on the header, we got a menu that gives us the ability to go choose the columns again or set a filter. But we're going to go sort descending. And then if I scroll up to the top, then I can see that there are a number of replicates and I can just click on them. So this is the first one, 103 rep 3, which we saw. And then there is this 108 rep 2, which we also did ourselves. And then there is this 159 rep 2, which I don't think we saw yet. 152 rep 3, 196. So that one's pretty darn close. But yeah, so Skyline, basically the way it comes up with truncatedness is if this peak boundary is all the way at the very last point, and the boundaries are within a few percentage points of the total height difference, it calls them truncated. So this is, you might still decide that this was something you wanted to keep, and if you did, you could just move this in 1 point or something, and then Skyline would no longer count that as truncated. But yeah, so you can see, you can actually see that you don't even need to click on those links. SkyJam will just kind of follow along as you change the selection in this results grid. Okay, so that's a quick look at the results grid. Lots more interesting uses. Actually, one more thing. Let's go back to this view and go to View, Edit View now. And I want to add one more thing. I'm going to add it to the end. So I put my selection at the end here. And I'm going to add user set total. And it actually puts it above that. And so I want to move it all the way down to the bottom. Well, actually, yeah, okay. All the way down to the bottom. So, so use the arrow keys to put it down at the bottom. User set total will tell us, has anybody tampered with this peak? Or is this just the peak that SkyJam chose? So click OK. And now we can see right at the top, yeah, these are user set true. Those are the ones that we set ourselves. We reintegrated. And there's another true down here, which is the one that I just moved slightly. And that's it. Otherwise, you know, SkyJam has picked truncated peaks itself. Okay, so that's a great way to look at the data. Let's close the results grid. Okay, so yeah, boy, we haven't made it very far. I'll say that I can actually process this data set in about an hour alone on a plane. But now we're showing you all kinds of tips and tricks. So here's the next. So we'll just go down to the next peptide. For the most part, this looks pretty good. Anybody see any problems? No obvious problems, I don't think. So then I'll just quickly kind of go through the replicates just to have a quick look at the data. And does anybody see anything in the chromatograms that they think is somewhat problematic? So, okay, yeah, go ahead. What, Magda?
There seemed to be this interfering peptide in the 154 replicate free.
Oh, okay, 154.
Actually, in all three replicates.
Okay, 154. So there, yeah. So it's this on this Y7 we're seeing some interference. There's also a really important thing about processing SRM data is when you don't have ideal selectivity. So ideal selectivity, all you see is your peak. It looks beautiful, and there's nothing else. But sometimes you'll see something like this over to the left. That, you know, that's another peptide, right? And those other peptides, those interfering peptides, when they don't coalute with your peptide, they still provide you with a landscape. And they have the same property of retention time stability as as your own peptide, as your target peptide. And so if you have chromatograms where you can see two other peptides on either side of your target that you're always measuring, and then your target peak goes away, but those two other peptides stay there, you can use that as confidence to say that, oh, your target peptide is not measurable, and it hasn't just like, you know, it's not outside the window. So, but the other thing is that they're dangerous because they don't all shift exactly the same way. And so if you have target peptides that are really close to your peptide, they can actually shift into your peptide. So in this case, there is almost always, if we look closely enough, there's almost always this thing that this is another peptide that has its most intense ion is Y7. And here's a peptide where its most intense ion is Y6. And if we just kind of look through all the transitions or look through all the replicates, you know, we can frequently see them. Sometimes they merge. The Y7 one merges so well that it disappears, but it's always kind of a problem. And so, you know, one thing we might choose to do is actually remove some of those transitions where we see interferences. So we might say y6 and y7. We could, if we really wanted to do quantitation on this one, we might decide just to get rid of y6 and y7 because we get less interference. And that, 3 transitions is definitely enough. So we could go on to our next phase with this. So we can go ahead and leave that like that. Otherwise, Skyline is integrating the right peak in all cases. So go on to the next one. This is pretty much the ideal ideal integration, right? And ideal selectivity. So if you're zoomed in like me, hit Shift F11, there is nothing else to select here. There is nothing you would count as a potential peak. You look down at this retention time plot, it's straight across. Let's go ahead and right click, normalize to none. So you can see that it's not completely consistent retention time. Here's a good moment to take a look at this retention or this peak area plot while it's denormalized. And so can anybody tell me something interesting that you notice about the data now when you're looking at the various replicates for a subject? Oh no, let somebody else answer. Come on. So what would you expect? 3 technical replicates for a subject. How should they look? If you could do the ideal experiment, how would your technical replicates for a subject look? Yeah, identical. And do they look identical? No. And so what is sort of systematically happening in all cases for this peptide, at least?
There's a pattern there that you see a systematic decrease from the first to the third.
Yeah, systematic decrease. We see this slope. So we seem to be losing signal, right? So that, just keep that in the back of your mind. It's gonna become important later. And so yeah, if we have technical replicates, we can learn stuff about the system. If these weren't technical replicates, would this mean anything? It wouldn't. If they're all biological subjects, then we cannot say, oh, we expect these ones to be like these ones. And so the fact that we have the technical replicates allows us to say, there seems to be a systematic degradation of signal over time of our acquisition. Okay. So anyway, we don't have exactly stable absolute peak area, but when we go back to normalize to total, we sure have really stable relative ion abundances. How do things look compared with our library? Is it exactly the same as the library? No, but does anybody think we might not have the right peptide here? No, it's pretty darn, that's close enough. I mean, we have a lot more Y3 signal, but there's a lot of signal out on Y11 and Y13, so it's not like it's dominated by Y3. And then another thing that we've said is in a lot of cases, it's almost, I think in this particular experiment, it's almost more important that we're just measuring the same thing every time. So does anybody have any doubt that we're measuring the same thing every time? No, we have this beautiful stable retention time. We have this beautiful stable ion abundance. We have measured the same thing every time. And so if there's a difference, even if when we order a synthetic peptide, this is not the peptide we think we're measuring, we can still find something scientifically interesting. Okay, so going on to the next one. Here are some problems. We might just say this is too problematic and delete it, but I think we can learn some interesting stuff from it. So where would, if you were just going to correct this, where would you start? Anyone? Where would you start?
maybe on the right, with
On
all
the-
these things which are out of retention time first.
Okay, we can start on the right with the big retention time deviations, and we can just click on them. And so let's take a look at one where we're actually doing okay, just to get a sense of what the landscape looks like. So what can people see in the landscape? Actually, I'm just going to click up here and kind of go down through it again. Can anybody see anything of interest other than our target peak? Is there any other thing that might be a peptide around? And if so, where? All right, I think there is another peptide around. Where is it? Yeah, 35.8, 0.1. So there's usually this other thing sticking around here, and let's learn a little bit more about it. If we zoom in, if I zoom into it, here it is. It's dominated by which transition? Y4, and there's a little bit of Y5 showing up, right? Okay, so now we have some idea of that. Let's go back and start looking at these ones out at the end where we have, not so great. So what is that? 33.9, dominated by Y4, a little bit of Y5. That's the other peptide. Where's our peptide? It's out of the window, right? So it's over here. It's like, so we have no measurement of it. The only thing we can do here is to right click and do remove peak, because we just did not measure it. We have no idea how big it was in that run, right? Okay, next one. Okay, what did we measure? Or what did Skyline choose? The second peptide. Where's our peptide? Oh, we can see it. So it was truncated. So I'm just going to remove peak. I could try to integrate that little sliver, but and then we can just keep going along. This next one, actually we got it, and the one after it, whoops. I can do one of these has. I guess I want to do Shift F11. Does that get me out? View, auto zoom, none. Okay. Well, I guess I have to scroll wheel it. So yeah, it's picked something. This time it didn't even pick our thing at 37, and here's our other peak is over here. And so we can go auto zoom, actually just, right click, remove peak. I'm going to switch out of here because I got in a weird zoom state. Okay, so, and we can just keep doing that with all the, directed interrogation again. We can just go through each one of these. You can see in most of the cases where there's something wrong, we either have a truncated sliver of a peak or no peak at all for Skyline to pick. And sort of as Ludovic was talking about, the software will just still try to figure out, well, what's the best thing? What's the most likely thing? And if we were using a statistical tool like mProfit that Ludovic was talking about, these peaks would be getting very low Q values, and because they are essentially just noise. But in this case, if we're going to manually process the data, we're just going to mostly just remove them. And I don't know. I'm not sure whether we would end up with enough measurements in this case to actually do statistics on this. I'm betting probably not. So maybe we really just wanted to. We may have just wanted to delete this thing. And then, I guess, is this that one? Yeah, okay. So, yeah, and remove peak. So fairly quickly you can get through and remove them all, and now you have pretty stable retention time and pretty stable relative iron abundance and a lot of missing values. And we can run statistics on that, and I don't know what that will tell us. But moving on to the next one, this one's probably so bad that I think it's not worth investigating. So I would just delete it. And then this next one, what do people think about it? How do things look over here? A little more variance than we've been seeing. Let's go ahead and denormalize. Right click, normalize to none. Yeah, probably this isn't going to turn out to be a bar marker, we now know, because it's pretty stable peak areas. How do people feel about the retention time variance over here? Looks kind of weird, right? It's like jumping around a lot more than we've been seeing. So, but again, I told you that these are not ordered in acquired time. So let's go ahead and sometimes when you see really jumpy retention times, it may just mean that there was a systematic drift, and you just have them out of acquired time order. So right click, order, and so you can see we have them ordered by document, which is just the logical ordering that we've put them in, with the disease first and the healthy second. And we can just go right click, order acquired time. And okay, yeah, now the retention time, there's kind of like starts getting later and then earlier, but you can see sort of a flow of retention time. It doesn't look quite so random, except for this one thing that I think if you look at enough of these, you would realize that, oh, this guy's always a little bit out. And if we had IRT normalization, basically I think everything in this run eluded a little bit late. I don't know why. All right, so I think that's probably about all that's interesting to look at there. Go to the next one. I'm going to right click, normalize to total again here. This is pretty much a one this is pretty much a one transition thing. I mean, it's got some signal on the other transitions. We could if you want to zoom into the y-axis and look at something closer up in the y scale, you can put the cursor, the same with the x scale, you can put the cursor on in the middle to the left or below either scale, and then if you use your mouse wheel, you can sort of scroll in just one dimension. And so when I look at it, yeah, okay, there's actual signal on those other things. They're not just flat. Again, it's Y3, 4, and 5, so the least selective transition. So I don't know how confident I am about this, but if it turns out it was interesting, I could order a synthetic and get more confidence about it. And I feel pretty confident that I'm measuring the same thing in every run, and there's not a lot else to measure, so I think I would just keep that and move on. And now I'm going to have us scroll all the way down to the bottom. So we could keep going doing that. That's a pretty simple process. We'll do a little bit more of it tomorrow. But I want to go down and look at these 3 peptides at the end, which are standard peptides. So those are global standard peptides. These peptides were injected in order to normalize everything else too. So the idea being that, hey, if we we have just said that we think that we might have systematic degradation, right? Signal degradation. We said from looking at those technical replicates, we were seeing that it was going down, and so maybe our standards will show us the same thing. Let's just first check on how they're integrated. So if we look at the bottom one, anybody see any problems with the integration here? I don't know, if you're a curious kind of person, you might click on this one and go, oh, yep, there's really nothing else, so I guess that's it. So that looks okay. Let's look at the next one. Anybody have any issues with how this one's integrated? maybe look at this other thing that's sticking out. This is, again, this is the one that I said is kind of always sticking out. Look at it, looks pretty good. You know, everything's quite good over here. So we're all, so first two, we think things are looking pretty good for us. Click on the next one. Anybody see any issues? Where are the issues? Other than these two. Not allowed to answer. Come on. Where? What? A lack of coelution. How do you know that?
I guess I have the wrong panel out.
What are you seeing that's telling you there's a lack of coelution?
I guess I'm seeing the wrong thing here.
Are you looking at this one? I'm going to zoom in and then they look kind of like they're coeluting to me. I don't know.
I have the wrong one on.
Oh, you have the wrong one. Okay. So if you're supposed to be down at this third to the last one, HLN GFSVPR. Anybody see anything that they think looks suspicious?
Intensity drops when you change normalization. You'll see that the intensity drops a lot.
Yeah, okay. So,
by the end.
she's jumping to the punchline. Yeah, so, and this is actually also sort of, we said that increased variance can be an indication of lower intensity. So we're definitely seeing some increased variance here too. But there's also something else going on here that's an indication of interference. Yeah, the Y4 keeps, the Y4 is getting we're seeing a bunch of Y4, and it can also be an indication of the intensity dropping because Y4 is just starting to contribute more to a smaller peak. So sure, let's go ahead and do what was suggested, to right click, normalize to none. She was quick on the draw, and boom. You know, we see that this peptide just about disappears. We can right click again and look at log scale. So right click log scale, and now that comes back, and you can kind of see that we go from 10 to the almost 7th down to 10 to the 5th or so. 10 to the 4.5. So yeah, so it ends up being a 200-fold change. And I'm going to turn off log scale because it can be kind of confusing. So 200-fold change. Like, is that, do we think that's likely reflected in all the other peptides? Probably not. I mean, we've been looking at things where we definitely didn't see 200-fold change. So 200-fold change is anomalous for this data, and probably is not, we should not use this peptide to normalize to, right? Because, you know, we saw everything else has some decline, but not 200-fold. So this is a bad choice for a normalization peptide. And ideally, this is, you know, setting up targeted methods. Ideally, we would have done an experiment ahead of time to test all these three peptides, and we would have done degradation experiments where we measured them 72 hours apart and knew that they were really good peptides. But we were less experienced in those days, and we kind of just chose three peptides. I think they were chosen to have some retention time spread. But yeah, they were not necessarily the best choices. So let's look at the other ones and see, you know, we want to have some global normalization peptide, especially since we can see that there's some systematic decline. So it would be great if we had something that showed us, you know, a nice systematic decline that we could normalize everything to, because we think that that's what's happening with a lot of our peptides maybe. Okay, so we'll look at the next one. Okay, that, you know, so this is a peptide that's injected, both of these peptides are injected into the sample at a constant concentration, right? So when we see this going down over time, that's signal decline in the mass spectrometry of the experiment. So this might be a good thing to normalize. Certainly that other peptide we saw had you know, similar decline over time, over its technical replicates. And then looking at the last one, that's also probably, you know, it looks like maybe it's okay to about here, and then it just really kind of drops off, and by the end this is a 20x signal decline. Not quite 200, but it's still, you know, more than we would like to see. Okay, so we're running out of time today, but we're kind of going to end things with these. Let's see. So let's see, where in the gradient do these peptides happen? So if I click this S up here, then now, whoops, can I undo all, zoom and pan? And now I can see that this HLN peptide comes out at about 13. AFG comes out at about 16, and this last one comes out at about 28. Does anybody have an idea how long a gradient this was? Was it a 30-minute gradient, or was it a? How would we look at the full range of all of our peptides? Well, this is a nice feature that if you can click on a protein and then get the peaks for all of the things in the protein in a little chromatogram graph, and maybe you've seen that already. It turns out that everything we select, Skyline, this targets view has multiple selection, and everything we select will show up in these graphs here. So if I want to see peaks for everything in my experiment, I can go Control A, and that will give me peaks. It's dominated by this TVS peak. So if I want to zoom down in a little bit, I can click on one of these, put my cursor to the left of the y-axis, and I can start zooming in, and hopefully I get down deep enough that I start to see some of these other things popping up. But yeah, so everything, it's probably more like a 60-minute gradient, right? Everything's between 10 minutes and 60 minutes. But this also tells us that those are two problematic standards are two of our most hydrophilic peptides, right? Let's go take a look at another way to look at these all of our peptides and what retention times they came out at. If we go down to this I'm actually going to pull out the retention time plot. And then if I right-click in it, I can choose to graph a peptide comparison instead of a replicate comparison. So right-click in the retention time plot, graph peptide comparison. And oh, I'm already sorted. So I don't know, you might not be sorted. So if you see something like this, how many of you saw that? Okay. So the way to get that to what I was seeing is to right-click and then choose order by retention time. And then now you'll get this full range, all of your peptides, how they're eluting, and we want to just focus on the beginning. So we can why doesn't it show me my little rectangle? I don't know why it's not showing me a rectangle, but I'm dragging out a rectangle just to see the beginning peptides. And then here I am. There's my HLN peptide. It's my fourth eluting peptide. Very hydrophilic. And then this is my AFG peptide, so it doesn't come too much later. So these are two very early eluting peptides. And now, all right, now I want to go look at the peptide peak areas. So I'm going to put this back by double-clicking in this title bar. And I'm going to right-click, I'm going to double-click to get the peak areas out, and then I'm going to right-click in the peak areas graph, and I promise you we're almost done. We're going to end close to schedule. So we want to choose graph peptide comparison. So now we get the peak areas for all the things. We actually get them by transition, and we want to switch to transitions. So right click, transitions, total, so we just get one line per peptide, and we even get a standard deviation bar sticking up, showing us this is the mean peak area. And we could go right click, order by peak area, and then we get a nice little graph here showing us our most intense things. And but we're gonna go back to retention times because we're interested in those early eluting peptides. So order retention time, and then drag out a rectangle to see the early eluters. Oops. I'm going to use the scroll wheel to the left of the y-axis. So here again, here's our early eluters. And what we're actually interested in is not so much their total peak area as their variance. So we're going to right click and choose CV values. Show me the CV values. And there they are. And this is our HLN peptide. What would be a sort of reasonable CV for the HLN peptide? Considering we injected at a constant value in all of our samples, what would we be hoping to see for a CV? Below, yeah, definitely, right on. Below 20%, if we were around 10%, it would be like, wow, you got great data. But if we're below 20%, we're doing pretty well. Not many things here are below 20%. Is that a problem? So when we say below 20%, we're talking about technical variance over something that's been injected at the constant variance over all of our replicates. What other sources of variance do we have in the other peptides? Are they all just injected peptides that we're just measuring technical variance, or what else are we measuring? Biological variance. So some of these, like, boy, we're excited that there's some variance because that means they might be changing. So we're not really holding them all to this 20%, but obviously HLN has a big problem. This one looks pretty similar. So I would like to now zoom in on LGP and see what was going on with it. I'm not that concerned that some of these are 50% or more variance, but I am kind of interested in what's going on with LGP. So I can click on LGP, and then I'm going to double click to put the peak area plot back in. So I've got LGP selected, and now I'm going to switch back to the replicate comparison graph. So graph replicate comparison. Whoa. So what do we think's happening there? So we've got them ordered by acquisition time, and we see this huge degradation. We see this huge drop. Let's order them by logical order again. So right click, order, document. Okay, now the groups of 3 are supposed to be exactly the same again, right? So this is a terrible peptide too. It's degrading in the autosampler. And so now you can see why at the MacLean lab, one of the things I put in the refinement phase of those slides I showed you, refinement. One of the things that we typically measure in these things that we're trying for even clinical assays is degradation. So once we get interested in a set of peptides, we will make sure they sit in their autosampler vials for at least 48 hours, maybe 70 hours in the autosampler at whatever temperature the autosampler is, and then we'll measure them, you know, at the start of that period and at the end of that period, and they should be very similar measurements. And if they're not, then they're not good candidates for quantitative assay. So in this case, this would not be a good candidate for a quantitative assay, and it would really be hard to get very good statistical, you know, if this came up showing that, wow, this is a really great biomarker, you know, I would be really dubious, because yeah, it's like you look at all of the high measurements, yeah, they're in the disease side, but that's just because the disease side was always measured before the healthy side, and things degraded so much. So okay, so we would want to just delete this one too. All right, last thing, we'll go down to these last set of peptides. So now we've decided. You can now actually, once we're ordered like this, you can see, right? So this is document order, and this is acquired time order. So we see the systematic degradation of our standard over time, and when we go back to document order, then we see that very pronounced sloping of over our subjects, similar to what we were seeing before. So this might be good to normalize our data against. So this is the only, of the 3 peptides that we could normalize our data against, this is the only one I would suggest. Ideally, we would have done experiments ahead of time to figure out you know, a really good set of peptides to do this with. We have one that may be left. We can now right-click and set standard type normalization. So if you select VVLS, right-click on it, set standard type normalization, then you get this little % signal that tells you, hey, this is being used as a normalization peptide. And now, select or open up this next peptide above the S. And what we'd like to see is a ratio, because now we're normalizing to something. And so, but to do that, in this case, you have to right-click and say ratios to global standards. And then now you do get a ratio. And you can do the same thing down here in peak areas, I think. Oh yeah, we can go to normalize to global standards in the peak areas. And so now, all of a sudden, that makes things... Yeah, for this is our first peptide out, it makes things look better, right? If I go normalize to none, I get that sloping. And then if I go normalize to global standards, you know, it's flatter among the 3 transitions. And that will be the end for today. We're going to come back to this data set. We have another hour and a half of working on with it. There's lots more interesting stuff to learn from it. But that's it for now. Save. Oh yeah, everybody save your document, because we're going to want to come right back to it. So save. And then you'll see that if I click new and then go file 1 rat plasma, it comes right back in the same state that I left it. So questions? Okay, great job, long day. Thanks for paying attention to the very end, and we'll see you tomorrow.